So my name's Jed Sundwall. I run our open data program at AWS. Oh, okay. Maybe not the right room for everybody, but so I run the open data program at AWS, and we work globally with customers who have data that they want to share. They want to get it in the hands of as many people as possible. And it's a very fun job, I can tell you. It's very interesting because, as you may have heard, security is job zero at AWS. It is our #1 priority, absolutely. And so most of our products, almost all of our products, are designed to make sure that your data is secure and stays within your account. And then my team and I, we get to go around and thinking, well, what if you don't want your data to stay in your account? What if you want your data to get out as far and wide as possible? And it's fun. It's a fun task to figure out these things out, as you'll learn throughout today's presentation. One of the sort of core concepts that we help customers understand and take advantage of is what we call this flipped data flow in the cloud. How many of you guys really like downloading data? It's awesome, right? So we increasingly hear from customers who are already dealing with massive data sets, or they know they're on the cusp of dealing with massive data sets. They're starting to deploy more sensors. They're instrumenting more systems and are producing much larger volumes of data. I get to talk about terabytes and petabytes all the time. I don't get to talk about exabytes that often. But it's really interesting talking about data with customers because it's a very abstract concept, data. And what is a terabyte? Do people really understand what a terabyte is? The way that I usually characterize these things is a terabyte takes about a day or two to download. If you had a pretty good internet connection, it would take you about a day or two to download. And then a petabyte is 1,000 times that. And mentally, a lot of people can't make sort of the leap to well, what does that even mean? It means that downloading a petabyte would take about 5 years. Okay, I have a 5-year-old son. That's crazy. Right? So the traditional mode of acquiring data by transferring it over a network or shipping disks and things like that is just really not feasible as we continue to deal with larger and larger volumes of data. So one of the huge advantages of the cloud is it allows us to flip that and let people bring their algorithms to the data rather than taking the data down to wherever they're running their algorithms and compute. You deploy compute next to the data. And one of the great advantages of this is the cloud is always getting better. We're building the cloud today. Being here at reInvent, you may be overwhelmed by the announcements of new products and services. When data is made available in a cloud environment, it actually becomes more useful over time as new services and features are added to the cloud. One day people woke up and suddenly they could use Lambda. Another day people woke up and they could use Athena. We're always releasing new instance types that have different kind of chips and GPUs and things like that that allow you to get more out of the data. But most fundamentally, what this does is that it allows your users, if they're consumers of your data, or you as a consumer of data, to spend more time doing what you actually want to do, which is analyzing the data and deriving insights from it. We actually have a term for this that we use at Amazon broadly. We use it a lot at AWS, though, which is undifferentiated heavy lifting. So it's all the work that you have to do that keeps you from doing what differentiates you and what actually gets you out of bed in the morning, what your actual mission is. None of you, if you're employing data analysts, you're not employing them to download data, right? You don't want them spending their time just acquiring data. You want them to spend their time deriving insights out of it. And we do have a website you can check out. It's opendata.aws, and you can learn about what some of our customers are doing, sharing their data in the cloud. Finally, I'm just going to make one note about our public dataset program. So we run a thing called the Public Dataset Program, where we work with public sector organizations, and actually some commercial organizations as well. It's a bit more rare with commercial organizations, but who have data that they want to get out to the world, and they want to experiment with us on new ways to make their data easier to access in the cloud. And so we will provide hosting for that data, and they encourage their community of users to work with the data in a cloud environment. And you can find the data sets that we have available at registry.opendata.aws. It's what we call the Registry of Open Data on AWS, or we call it RODA for short. And you can browse data sets by tag. We organize them there. You can also search for them, and you'll find all sorts of data. So we have a satellite imagery tag that you can use to browse all the satellite imagery data sets that we have. And I'm going to stop talking now and hand it over to Anja from Synergize. But as Anja speaks, and then also Clive Charlton, my colleague from the Africa Solutions Architect team, are going to talk about applications that have been built on shared data in the cloud. And the applications that they're going to discuss are built on top of these data sets. So everything that you're going to learn about today, you're going to learn about applications that have been built on top of data that's publicly available that you all can work with today on AWS. So thank you again for joining us. I really appreciate you all coming out. Thanks.
Thank you, Jet, for inviting us here and giving us opportunity to present how we utilize the Earth observation data available on AWS. So I will present our way to monitor the Earth without hosting the world. And I will start by just a short history of Earth observation at scale. So I will briefly describe the satellite and the data that they provide, and some of you might be familiar with this, so I apologize. I will name a few technical challenges that we need to overcome in order to efficiently utilize this data. And I will try to explain this through a use case called Blue Dot Water Observatory. And I hope that at the end of the presentation, I will convince you that we live in very exciting times. So today, we have a lot of data available, services that make this data discoverable, easily accessible, and everything on the cloud infrastructure that can realize your ideas. So what we need actually is just your ideas in order to make good things. Okay, so let me start with a short history. So the Earth observation has a rather long history. The Landsat program is the longest running program, acquisitioning imagery of Earth. It started almost half a decade ago, and its archive consists of more than 5 million acquisitions. A notable event took place in 2008 when United States Geological Survey opted for open data policy. This led to immediate increase in number of downloads and also give rise to development of scientific and operational services that serve governments, private companies, and civil society. And for example, in 2017, 20 million acquisitions were downloaded alone just from the official Landsat archive. Then the data itself doesn't have a lot of value. The value is hidden in the information that this data can provide. In order to process these large amounts of data, you need the resources. And this became easier in 2015 when AWS introduced this open data program. And just in first year of availability of Landsat data on AWS, more than 1 billion requests were made. So there is really a demand for this data. Luckily for all of us, a lot of other governments followed the lead of USGS and opted for open data policy also for data provided by their satellites. So at the moment, we have a lot of satellites providing open data, which is available to all of us. They have different properties, so they can serve a lot of different use cases. These satellites commissioned by governments are usually large and expensive to build and to launch. But in recent years, it has become really affordable to build and launch a smaller satellite, so let's say up to 10 kilograms. So we now are witnessing an exponential increase in number of satellites being launched each year, and this will just continue. And so in the future, we will have just more and more data available that we can use to monitor the Earth. The satellites that are currently available, or that provide data that is currently available, come in different shapes and sizes. So they can be only 4 kilograms, and they can weigh only 4 kilograms, like the Dove's planet, or several tons, like Landsat 8, for example. By the way, it is only important for the owners who have to pay for the ticket to orbit. From the user perspective, other properties, of course, matter. The first one that we all notice immediately is the spatial resolution. So here, these 6 images show the same area of Wimbledon tennis complex in London at different resolutions. On top row from the satellites that provide open data, so this is usually of lower spatial resolution, and in the bottom row from proprietary sources, satellites that provide usually much better resolution. But even with the open data provided by Sentinel-2, so the 10-meter resolution, you could already see and recognize the main buildings of this Wimbledon tennis complex. But at the lower resolution, so a few meters, you can then recognize individual tennis courts. And at 30 centimeters, which is currently the best, you could see, probably see tennis players playing tennis on each of the court. But of course, everybody would like to use the best possible resolution, data with best possible resolution, but this comes with a cost, necessarily the cost associated to the image that you need to pay to acquire the data, but also to process this data. The image at 30 centimeter resolution has 1,000 times more pixels than the image at 10-meter resolution. And to process 1,000 times more pixels, it costs. But depending on your use case, other properties are important as well. First one is, for example, the temporal resolution. This simply tells you how often you can get an image of the same point on Earth. So it can range from 1 day, like in case of MODIS or doves from Planet, or it can be up to 1 week, or like in case of the Sentinel-2, or 2 weeks, like in case of Landsat 8. The other important property is spectral resolution. Human eye is sensitive only to visible resolution, but sensors on top of the satellites usually record more data. And this additional information is crucial, for example, when you want to monitor vegetation or when you want to detect water and so on. And here, where open data satellites usually cover a wider range. What open data, or data from satellites that provide open data lack in terms of spatial resolution, they definitely compensate in terms of accessibility. So actually now we can get imagery just hours after it has been processed at their source. So everybody, thanks to AWS and tools like EO Browser, anybody now can monitor the Earth and observe what is going on in their neighborhood or globally. And people are doing that. So users are preparing visualization like this that actually change our perspective of Earth. So we can see seasonal changes. We can observe devastation caused by natural disasters like Camp Fire that was raging nearby in California last November. Or we can observe in near real time the deforestation that is taking place in Amazonia. And this is brought to our attention just by users who care about what is going on Earth without them necessarily have any remote sensing expertise. And there are many of such users. So EO Browser, for example, had in April 30,000 users that made over or almost 30 million requests. Data that is available on cloud infrastructure also empowers researchers, not only the individual users. Researchers can now do things that were simply impossible to do maybe a couple of years ago or a decade ago. So here is an example of Global Surface Water Explorer developed by Europe's Joint Research Center in collaboration with Google. They have processed almost the entire Landsat archive and quantified the changes in global surface water for the last 35 years. In Blue Dot Observatory, we aim to provide a complementary information to this, but we will see details more later. So now let's talk about the technical challenges that you need to overcome to deal with this data. It may sound ridiculous, but for a newcomer, it may be even very difficult to locate the data that they are interested in, so the data that intersect with their area of interest. The Earth observation volumes are very large, and there are many. So usually, the good thing is that you just rely on already available services that help you discover the data and that are conveniently described on AWS Open Data Registry. Once you find the data, it's usually in the format that is most probably unfamiliar to you. So there is no standard yet for Earth observation data. But recently, development has been made, and new data formats emerge, like cloud-optimized GeoTIFF, which make it easy to work with them in the cloud. So once you are able to process the data, in order to make it more accessible and usable to the end user, you usually need to dice the large acquisitions provided by the satellite operators and stack these pieces in a temporal stack to produce so-called data cube. This will be the topic of at the end of this session given by Clive. Alternatively, you can use web services which hide all the peculiarities of dealing with the data. So the user only needs to understand what the API can provide, how to use it, and then you can use different data sources and so on, and always get the data back. So it's really efficient and fast. And the user of Sentinel Hub API, like an example, just needs to worry about or needs to specify what kind of data he would like to use, like, for example, true color visualization of Sentinel-2 in this case, for what day in the year or what time period, of what area of interest, so provided by just the bounding box in specific coordinate reference system, and then some additional properties like in what is the desired resolution and in what type the image should be returned. So the user really doesn't need to worry about downloading, stitching, mosaicing, metadata parsing, anything. You just, with a single request, you get data back immediately. So, and this brings me to Blue Dot Water Observatory. I'm pretty convinced that without services like this, like Sentinel Hub, Blue Dot Observatory wouldn't exist. It wouldn't be possible to do it in this way. The idea for Blue Dot Water Observatory was triggered by the Cape Town water crisis in spring last year. At that time, media around the world were full of images like this, showing the images of reservoirs before and after the severe drought, so before full and after almost completely empty. At that time, the satellite imagery was also already quite accessible, so we were also seeing time lapses like this, showing the process of drying up of the reservoir. So as a data scientist, when I see images like this, I couldn't help and wonder why is satellite imagery not used to monitor the water bodies, so to monitor the surface water area of reservoirs. And just by testing, for example, on this water body, Theewaterskloof Dam in South Africa, we figured out that it's actually quite easy to do that. And then looking, investigating whether such services already exist or whether it's possible for the users, for people of Cape Town to check what are the current surface water, what are the water levels of their reservoirs, we could only find dashboards like this where they just summarized the current water levels without any context, so without any historic context, anything. Luckily, the Cape Town avoided the day zero and the water crisis, so the water levels are back to normal now. But another crisis emerged in India. So the city of Chennai, which is the sixth largest city, has reached day 0 in June this year. So since then, they don't have any running water in the city. And unfortunately, we will witness more and more such crises in the near future. For example, the World Economic Forum even ranks the water crisis among top 10 societal risks. So it's really important that we can provide government agencies, city planners, water authorities, as much information as possible, which can help to prevent such crises to appear in the future. And one such service is already mentioned Global Surface Water Explorer. Here, in this map, you can see, and the map displays water occurrence as determined from the data from last 3.5 decades. So the blue pixels are almost, or were almost always covered with water in this time span, while the pinkish or transparent pixels were seldom or never covered with water. So if you click then on a specific point, you can get even more detailed statistics for that specific point, like monthly water occurrence. Unfortunately, this service is not updated regularly, so you cannot check what is the current state, what was the state last week or last month. And in addition, it gives information just for specific points. You cannot get information for objects like water bodies and so on. So here is there when Blue Dot Observatory can also add some additional information. But the process of building this map is very time-consuming, or it requires a lot of resources. So the authors claim that they spent 10 million hours of compute time to produce this map. And just out of curiosity, I wanted to check what is the cost associated to this. And just rough estimation yields around $500,000 to $1 million. And this is just, I mean, it's something unimaginable for me. And these numbers, when I see these numbers, they scare me off because they make me believe that Earth observation data or services based on Earth observation data can be or are available only for organizations with unlimited resources, so that as an individual or a small company, you can't do anything. But this is far from truth. So in order to make a service more affordable or cost-effective, of course, you don't process the entire landmass. You can focus only on the region, on the area of interest. In case of Blue Dot Observatory, we want to monitor specific water bodies. And these water bodies intersect, or the data is provided in single satellite acquisitions, which are still typically large. So if we would use these single acquisitions, we would still need to process a lot of data unnecessarily. But if you just focus only on the area of interest or only on the water body and its surrounding, which can we do by utilizing services like Sentinel Hub, then we can really minimize the amount of data that we need to process. So, and as such, also minimize the costs related to this. So the entire pipeline to determine the surface water level of any water body at Blue Dot Observatory is rather simple. In the start, we simply need only the polygon outlining the water body of interest. And we can take this polygon, or we can find them, for example, in OpenStreetMap. Once we have it, it's very easy to request data for this area of interest using Sentinel Hub. Remember, we just need to know the bounding box and time interval, and the bounding box can be easily determined from the polygon itself. So here we request, for example, true color for visualization purposes, but the algorithm itself uses something that we call normalized difference water index. So this is nothing but single channel image that kind of enhances presence of water in the image. The detector itself is very simple. It consists of canny edge detector and adaptive Otsu thresholding. And once you combine these two steps together, the algorithm converts this grayscale image to a binary water mask, binary water, not water, mask. We vectorize it, and we keep only polygons which intersect with the nominal outline of the water body. We can then calculate the surface water level, so we cannot calculate the volume of water, but just the surface, which is given by the detector water area divided by water body area. And we store both of the measurements, so the detected, extracted shape of the water and the level itself. And once you do this for the entire time span, then you can really start to see and observe what was going on at that time of the crisis, of Cape Town water crisis. So we saw that in the rainy season of 2017, so at the end of the season, there was not enough rain which would fill the reservoirs up. So so they eventually almost dried up. But luckily, the situation improved later this year, last year, and this year is even better. So now that we have this process on a single water body, it's very easy to scale it up to thousands or 10,000s of water bodies. What we simply need is the database of water bodies and with the nominal outlines. So this process was very time-consuming to create such a database. We heavily depended on already existing ones, like Global Reservoir and Dam Database and the one from World Wildlife Fund. Unfortunately, as the two images here indicate, the outlines of water bodies in these two databases are not precise enough for our use case. So we replaced them with the ones taken from OpenStreetMap, and we manually had to exclude a lot of water bodies because they were not interesting. The Blue Dot Water Observatory currently makes weekly updates of water levels for more than 13,000 water bodies globally. And AWS, from the point of view of AWS services, the process is really simple. So we just used Amazon CloudWatch to trigger a Lambda function, which in turn starts an EC2 instance. EC2 instance is set up in such a way that starts the process of updating. So the process requests for metadata from stored on S3 storage, gets the relevant data, so the satellite imagery from Sentinel Hub, determines what is detects the water, determines the surface water level, and stores the results back to S3 storage. The client that uses the dashboard to check what is the state gets the observations, so just the polygons and the numbers from the S3 bucket, and the imagery itself, again, via Sentinel Hub. So we actually don't need to store any satellite imagery, and by this we can also control and keep the costs down. So it takes rocket science to put satellites to orbit, but it definitely doesn't take rocket science to extract information out of the data that they provide. So once we have everything together, we can now also start to see, or the benefit is that you can check what was the situation in other water bodies near Cape Town. So you can really, or the users can really build more insights on what is going on with the environment, with the water resources in the neighborhood or globally. So if we take a look at the Chennai water crisis, we also see that here again, a drought, insufficient monsoon rainfall for 2 years led to the water crisis that is ongoing there at the moment. So since we are in Las Vegas, I also added a water body nearby, so this is Lake Las Vegas. So here the trend is really boring, so it's constant. But But this is a nice thing, so we would like to see more of this. So this is really great. But if you then start to browse in the vicinity, if you go to California, you can find much more water bodies that exhibit seasonal variation. If you then spend a lot more time browsing through all the observations, sooner or later you will find examples like this where the simple algorithm actually fails. So these two here, we highlight the observation that is clearly off. It's wrong, so it's not perfect. But our approach is that these imperfect results should not prevent us to share good results with the users. And we can actually ask users or get feedback from the users to fix the faulty observations, and in this way help us to build better algorithms. So this, for example, is possible also with a classification app tool that we developed, and it's quite general, so it can be also used for another use cases. So before I give the floor to Clive, I would just like to point out a few more facts about Blue Dot Water Observatory. So the service is based on currently Sentinel-2 open data available on AWS, which amounts to around 5 petabytes of data. It makes weekly updates for 13,000 water bodies around the globe. And in total, so far, it's made around or over 2 million observations. It's also interesting to see what is the cost related to this. So cost of operation for around 10,000 water bodies amounts to around 5 person weeks of effort. And the most time-consuming part was actually curation of the water body database. Then the initial process took around $400 so to process everything up to that point, so the entire history of Sentinel-2 imagery available. And now that we are in the, let's say, automatic updating phase, it costs only $10 per month for cloud infrastructure and another 100 for Sentinel Hub subscription to get the data. So now if we scale this up to, let's say, 100,000 water bodies, so again, the most difficult part would be the curation of the database, but then the costs of ICT would be really low. So $4,000 for initial processing, but then for the service to be alive, to provide the data, to make weekly updates, it would cost just a couple of $100 per month. So I hope I convinced you that it really does not cost the world to monitor the Earth. And if you want to get more information about services or more stories about this, check these links. Thank you. So.
Thanks, Anze. Thanks very much, everyone. My name is Clive Charlton. I lead the solution architecture team for Sub-Saharan Africa for AWS. And I live in Cape Town. So this is really an inspiring story for me. I lived through this drought. And it's fantastic to see the innovation coming out of these kinds of things. Just out of interest, is there anyone from Africa in the audience? Yay, you've got a couple of people here. Cool. So what I'd like to talk about is Digital Earth Africa. AWS and Amazon Sustainability Data Initiative are really proud to be the technology provider behind Digital Earth Africa. The aim of Digital Earth Africa is to track changes in our environment over time. And by doing that, we start providing insights into government. We've had a wonderful example of the Blue Dot Observatory, creating insights about droughts, but this could also be used for floodplain analysis, food security, water security, land use, and you know the uses could be endless, which is fantastic. Digital Earth Africa is established in Addis Ababa in Ethiopia. We'll be opening offices there soon, and the whole process is about creating decision-ready products across the continent. Digital Earth Africa was established in collaboration with the Government of Australia and Australia's Geoscience division where they'd originally created Digital Earth Australia, which saw fantastic success. They also took insight from a program that was launched last year, in May last year, called the African Regional Data Cube, which was a collaboration of five countries in Africa, which was Ghana, Senegal, Sierra Leone, Tanzania, and Kenya, using satellite imagery to look at Earth observation for the region. So I think Digital Earth Africa is more than just a technology. It's also about creating a community. So they use open source technology like the Open Data Cube, and then also open data, as Jed had described, moving this data into the open data platform, and really creating a community around how Earth observation can be used for insights around Africa. The Open Data Cube is all about ingestion, storage, provision, and analysis of structured geospatial data, and creating time series of satellite images. So exactly as we saw with the Blue Dot Observatory, looking at the time series of data of satellite imagery. So it's about creating a continental scale platform, rather than just looking at a smaller subset of countries. This is for the entire Africa, creating a data cube for the whole of Africa. The Amazon Sustainability Data Initiative will be providing data sets like USGS Landsat and Sentinel-2 in the Cape Town region. So I'm really pleased to announce that Digital Earth Africa will be one of the first organizations moving both their compute and data into the Cape Town region, which will be going live in the first half of 2020. So it'll be a fully African solution, both hosted in Africa, developed by Digital Earth Africa for Africans. And it's around really creating the insights for government and empowering governments to make informed decisions using decision-ready products like Digital Earth Africa. And that creates sustainability for our environment into the future. So just a short coverage on Digital Earth Africa, but I wanted to thank you very much for your attention and your time today. Please complete the app session. So we do have some time for some questions. So if anyone has some questions for any of us, please feel free. Oh, thank you.
Thank you.
Thank you. So I think there's a question at the back there.
Second question, like you said, the volume couldn't be determined from the image. So, simple question is like, is the shade of the hue of the water bodies, could it be used to approximate the depth and therefore volume?
So if I answer first the second question, so there are ways to extract also volume. It involves also usage of other data sources or information from other kind of satellites like radar. So not only optical, but also radar data. Or if with the optical only, if we would have a very precise digital elevation model for that area, for the water body of interest, then we could also estimate the volume. To answer the first question, I hope I didn't say that we could prevent droughts. What I meant is that with this, the information given here can be used by users to gain better understanding of what's going on and to put current situation in the more historic context. So a lot of water bodies, for example, exhibit seasonal changes. And sometimes you see almost empty water body, but you see that this is seasonal, that this happens every year. But once, if, for example, then in this year, there is not enough of rainfall, and the water body doesn't fill back during the rainy season, then you know that next year, you could have troubles, and you perhaps start taking actions sooner.
Yeah, and perhaps maybe about creating early warning systems.
Yep.
So, you know, with enough information in advance, governments can take action, you know, to prevent, not prevent, but at least provide solutions to disasters in those areas. Any other questions? Sorry, we're here on the side.
I'm curious, how far back in time does your data set go? Did you start the clock with the launch of Sentinel?
Yeah. So it would be possible to extend it by using Landsat data. Yeah. But so far we haven't done this. But yeah.
And to add to that, within our public data set program, we have the entire Landsat 8 archive, but just Landsat 8 for now. And kind of selfishly, I have one more question. Do you have an API?
Yes.
From Esri. So just curious, if you guys have any plans to, referring to this person's comment, on exposing API for people to query data, spatial temporal data, more easily. I don't know if you heard about the stack, spatial temporal asset category. Is there any plans for that?
So at the moment, all the observations done by Blue Dot Observatory are publicly available or open. So everybody, just if you know the ID of the water body, you can easily get both the surface water levels and the extracted area of water, so the shape. So this is,
That's through Sentinel Hub.
No, this is just the Blue Dot Observatory alone. So it's a the dashboard actually uses the same API and it's open.
And then from our end, I mean, so we love Stack. You know, I think the approach that we took with Landsat, and I can sort of share a little bit of the backstory there. Is that when we started looking at Landsat initially, we knew that our customers, including Esri, and we actually worked very closely with Peter Becker from Esri on this, would appreciate having easier access to Landsat in the cloud. And you know, we looked at the way it was being distributed via TAR archives, where you download about 1 gigabyte of data. And we talked to so many people and learned that very few of them needed all of that data. You know, they usually are looking for 3 or maybe 4 bands at a time. And so the first obvious thing was like, well, let's make the data available on a per band basis, just as objects in S3. And let's just use the S3 API as the API, right? You know, S3 is very performant, it's very powerful, it's very simple. That's what the first S in S3 stands for. But it really does the job. And it was Peter who encouraged us to convert the data so that it could use internal tiling, which allows you to home in on a certain tile within the scene and not get the entire scene. And that's really what kind of like opened the door for applications like Sentinel Hub to be able to use Lambda functions to go into these data sets. So it's a little backstory there. But that, I think, laid the foundation for Stack, right? So like Stack is really built with a cloud-based object store in mind, and this is sort of approach to sharing data that gives you sort of the foundation for the Stack API. So our thoughts on this right now are that, you know, Stack is perfect. It takes full advantage of S3 and of object storage APIs on its own. If there are any other services that we could potentially build on top of data that's shared, you know, following the Stack spec, that's a cool idea, you know, but we don't have, you know, first of all, we don't comment on plans. So I'll leave it there. You first.
You talked about when most of the work in the Blue Dot Observatory was taking the shape of the water bodies from the global reservoir and dam database. What was the work involved in did you have to translate that data into a GeoJSON format?
No. So, no, The most effort went into, so this global dam and lakes reservoirs is already very cleaned up. So this was a source that was really useful, and we could use it very quickly. The only problem with it was that the outline of the water bodies was not precise enough, so we had to replace it with the ones taken from OSM. That was, I mean, it's technical issues perhaps, but it's solvable easily and quickly. But it consists only of around 5,000 or 6,000 water bodies around the globe, and we want to add more. Then we found this wildlife, the other source, and it has much more. It has, I think, up to 300,000 water bodies, but it includes also rivers, wetlands, and water bodies that don't fit into, let's say, water body observatory, and this had to be cleaned up to some extent, and this involves manual work. And this is then time-consuming.
There's another, you got a question? No, we're good.
Yeah.
How do you do that? That's the first question. And then second question for yourselves in AWS, is there thought of maybe having like a marketplace for large organizations to put money into, so open organizations can spend through those credits. So we get tax benefit, they spend from there. Is there, that's
Okay, well, no, I like that idea, but yeah, so you go first.
So from
Yeah, repeat the, repeat the question.
the first question was about the AWS services that we use. Since they cost so little, whether we try to optimize it in any way. Answer is that in the beginning, when we planned, we made really more convoluted plan. We were thinking also using Lambda, and we, in the beginning, actually used also DynamoDB. But then eventually just we ended up with very simple setup. So we have a single EC2 instance that is triggered, does the computation, and then shuts down. And all the results are stored on S3 bucket. And basically that's it. We could replace it with a Spot instance, but so far there was no need to do that.
And then, so the second question was, are there any plans to sort of, I think about this stuff all the time.
like carbon credits, but
Yeah, so like, could there be a way that like, people could fund an organization that works on, distributing data, making data available, and perhaps it could be a nonprofit, but it'd be a way to sort of contribute towards ensuring that these data sets or services are available. Is that a fair characterization? And the compute to make it happen. So I think about this kind of stuff all the time. So this is, what I'll say is like, no, we don't have plans. This is a big idea, but I'm glad you brought it up because it comes up over and over and over again. There's a huge challenge in terms of business models for how to open up data sets at this volume, right? And one of the issues is that the governments that produce these data sets, it's very hard just to produce these data sets. That's a hard enough job. And increasingly, they're faced with, because of open data policies, that they have to get that data to anybody. So they have a much larger and much more diverse audience coming to work with the data. Good examples like advertisers want to get weather data now because they can use mobile data and weather data to trigger very custom ads. So so suddenly NOAA has to deal with like advertising companies. So that's really hard. And so we do see the need for entities that can serve as kind of like an intermediary, and sort of share this burden and things like that. So anyway, it's this idea is in the air. A lot of people are thinking about this kind of stuff. I saw some other hands come up over here.
Yes, there's the lady over there.
So the Earth is a closed system, and there's X amount of water that doesn't leave. So you can see where droughts are. I imagine you can also see where flooding happens. Has anybody been able to make a connection? Like, okay, there's a drought in Africa, and the way the jet stream goes, can we predict a flood somewhere else? Not that you can move the water from one
Yeah.
Is there anything like that, any predictive?
It's interesting.
Yeah, way of
idea.
everything, but
Yeah, my comment would be, answer would be that the data is available. So if somebody has an idea like this and wants to check, and then by all means, use the data.
All right, then we'll do the last question. Yeah. I think.
Curious
Yeah.
what the long-term funding strategy is and maintenance strategy for the data on AWS.
So the way we do it is that we have our customers who have data that they want to share. They enter into an agreement with us for 2 years, where we say, we'll provide hosting for this data, and then that agreement can be renewed. I can say that we've never discontinued one of these agreements. They always get renewed. Now, but there is the option that if we have data sets, for example, that just never get used, then we might consider deprecating those. But that's historically the way it's been. And the reason the program works is that we say data has gravity, right? So if we have useful data in the public dataset program, it attracts compute usage, which justifies us providing the data like that. Okay.
Cool.
Well, we're here for a little bit, so thank you so much.
Thank you very much.